Cool.
This meeting
Yeah.
is being recorded. That's
Okay.
excellent.
So we just got the
Wonderful.
prompt.
All right.
So, yeah, so shall we?
Hi, I am here. I'm recording.
Hey,
Very good.
hi, Celia.
Hi, Chris.
Is it being recorded just because you showed up, or?
Yes,
because-
I can see it. It was automatic to
Okay.
start recording.
Yeah, actually, you can set it up to automatically do that right when you join in. So cool.
Wonderful.
So should we give it a minute or you want to start?
Give it a minute.
Okay.
Thank you to the students who are here today. We're really excited to see you.
Yeah, and we said that we would like we want to set it up such that this becomes a recurring situation where industry partners follow up with the students based on the presentation or the labs, the national labs. That's what we would like to do.
And for the students, if you have time, I know we've squeezed a lot into 1 hour. It would really be interesting, I think, to some of us to know what your plans are. Finish your research. I know everybody's really busy. I had another meeting that I had to bow out of, so it's always people trickling in a little late. But Chris, I know you want to make a little intro, so if you want to get started, I'll
Yeah.
let you guys take it.
Okay. Great. Well, so yeah, I'm delighted you're all here. Welcome to the QED-C poster session. By way of quick introduction, I'm Christopher Bishop. I'm a workplace futurist, a TEDx speaker, a LinkedIn learning instructor, and a former IBMer. And I recently joined the QED-C Workforce TAC, delighted to be a member. I'm the master of ceremonies at a virtual event called Inside Quantum Technology. I invite you all to join us. It's taking place May 17 through 20. We're doing it virtually. It's a 4-day event focused on topics around quantum information science. Again, delighted to be hosting the poster sessions today. We have 4 talented researchers who are going to share their work. Let me take you through a couple of slides quickly and then we'll begin. So for those of you who might be new members or just as a refresher, the QED-C is tasked with enabling and growing the quantum industry and supply chain at a meta level, right? So our objectives are to identify and address gaps in technology, benchmarks and standards, and germane to this conversation today, workforce, right? So we have 150 members from industry, academia, government, other sectors. Today, we're focused on this aspect of QED-C, connecting students and industry members. So quantum jobs are posted on this site. Here's the URL, quantumconsortium.org. There's a downloadable database. We encourage you to take a look at that. Students looking for internships or full-time employment. It's posted on the member website. These e-poster sessions are going to be ongoing. We're going to be doing this frequently, so stay tuned. If you have suggestions for connecting students and QED-C members and industry, please send them to Adrian German, who's the chairman of the Workforce TAC. So there's his email address. We can put it in the chat as well, so if you need to refer to it. We have 4 brilliant researchers presenting their work, sharing their insight today. Billy Strickland, Mitchell Yothers, Dengyu Yang, and Patrick Kelley. So without further ado, let me introduce, hang on, let me get my notes here. Our first researcher. Okay. So Billy Strickland. Billy's a physics graduate student in Professor Javad Shabani's group at New York University, the Center for Quantum Phenomena. He works primarily on material synthesis and characterization and is broadly interested in the applications of different types of materials for quantum computing platforms and circuit elements. So Billy, welcome. Please share your work with us.
Cool. Thank you, Chris. Okay. Yeah, thanks for the introduction. So today I'm going to be talking about reactivity studies and the growth of strained indium arsenide aluminum heterostructures. So this work was funded by the Army Research Office, and done in collaboration with researchers at IBM Quantum. So in our group, we focus mainly on near-surface indium arsenide quantum wells, and we grow these by molecular beam epitaxy, and we're able to contact these with a thin aluminum layer for a superconductor. And doing this in situ, like in the growth chamber, we're actually able to get a nice interface between the aluminum and InGaAs and indium arsenide layers. And this is seen in the TM image here by an atomically flat interface. And what's more is that what's seen here is a simulation of the electron density and is very well confined in the indium arsenide 2D channel. But also you can actually get a non-zero value of the wave function at the InGaAs aluminum interface at z equals 0. So at this interface, you can get some overlap of the wave function. And this could be very useful for types of overlap of the semiconducting and superconducting phenomena. And some of the devices that this can be useful for are in gate-mon qubits. So a gate-mon qubit is basically a transmon, which has its insulating weak link region in the Josephson junction replaced by a semiconductor. And doing this, you can actually apply a gate voltage to the weak link and vary the supercurrent through the junction, effectively changing the transition frequency of the qubit. So these types of qubits can be pretty, people are optimistic about these types of qubits because detuning qubits from each other using the gate voltages, you can actually lower the amounts of crosstalk between qubits. Unfortunately, as can be seen by this plot, which shows the lifetimes of superconducting qubits over the years, gate-mon qubits aren't performing as well as modern superconducting qubits. So their lifetimes are hovering around the 1 microsecond to 10 microsecond range. So what limits gate-mon qubit lifetimes? So there are a couple of reasons. One of them is the charge noise that you're reintroducing with the gate electrode coming over the qubit. This is kind of inherent to the gate-mon platform, and we can't really do much about it. But there are some things that we can do, and these come mainly in the materials quality. So number 2 here is defects in the 3,5 bulk. So in the indium arsenide layer, we usually grow this on an indium phosphide substrate. But to do this, you have to gradate the composition from that which is lattice matched to indium phosphide to one which is lattice matched or near lattice matched to indium arsenide. And we do this using a 1 micron thick graded inelastic buffer layer. But in gradating the composition, we actually introduce a lot of defects in the bulk in the form of misfit and threading dislocations. And these can be bad for microwave. These can be channels for absorption, which are not good for making resonators on. Some other things are the lossy indium phosphide substrate. So indium phosphide is known to be piezoelectric and convert microwave energy into mechanical energy. And moving away from indium phosphide could be a good tactic in the future. And the last is this recontacted sputtered aluminum process, where you have this qubit island, but in reality, you're actually etching away everything around the qubit island, and then you're defining your microwave circuit down onto the indium phosphide substrate. And to do this, you have to have this etch and recontacting step, which can lower your the quality of your microwave circuit. So to combat these limitations, the first thing we do is address directly the defects in 3,5 bulk. What we do is we eliminate the graded buffer layer, as seen going from this taller structure on the left to this middle structure. This middle structure, you have just a constant composition of inelas, and you're straining the indium arsenide and the aluminum layers to that underlying inelas, which is lattice matched to indium phosphide. But this has a couple problems associated with it. One is that can you actually grow an epitaxial aluminum layer on this type of structure? And another one is you're actually increasing the Schottky barrier height. So as you add gallium to this top InGaAs layer, you increase the Schottky barrier height at the surface, and that actually makes it harder to get the conduction band to dip below the Fermi level and get electrons in this indium arsenide channel. Okay, and then in the future, we would like to move towards silicon substrates, but these have a list of problems in themselves. Maybe the topic of a future talk. One is the large lattice mismatch between the 3,5 layers and the silicon, and then the other one is polar on nonpolar epitaxy. But for the purposes of today, I will be focusing on the growth of this middle structure. So some of the problems of growing an aluminum layer strained to the underlying indium phosphide substrate can be summarized in this plot, which shows the strain energy as a function of the indium content or the composition. And you can see that there's a minimum of the strain energy on the aluminum layer near 0.8, but as you go away from 0.8, so near where your lattice matched indium phosphide, you actually have a strain energy which is near double of what it is just on in-gas 0.8. And the same can be seen on the other end if you grow aluminum directly on indium arsenide. So we've conducted these types of studies before where we've grown aluminum directly on indium arsenide, and we found that you have this really large reaction between the aluminum and indium arsenide layers. You get this aluminum islanding on the order of like 50 nanometers and indium arsenide pitting of about the same size. And yeah, this just signifies that there's a large reaction between these two layers, and this is not ideal. So what was found in this paper and what we showed was that you can actually introduce intermediate aluminum arsenide layer that will limit the diffusion between the aluminum and indium arsenide. And as you can see in this TM image, we're able to get nice epitaxial aluminum sitting well over indium arsenide with this aluminum arsenide in between. And we've also conducted AFM studies of this, and we've varied the different kinds of barriers in between the aluminum and indium arsenide layers. So with the sample of aluminum directly on indium arsenide, you have a RMS roughness of about 1.3 nanometers. Whereas when you introduce these intermediate layers, you can lower the RMS roughness to 0.9 nanometers and 0.8 nanometers, where the best sample is shown on the right with the aluminum on indium arsenide with this intermediate aluminum arsenide layer. But a problem with this is that you actually can't get a conducting TUDEG, or this sample was not conducting, and this is a problem when you want to make gate 1 qubits on it. And to study this, we actually went back and tried to simulate the charge density and conduction band energies. And we found that you actually have to have a thicker in-gas top barrier in order to get the conduction band to dip below the Fermi level and start occupying electrons into the conduction band. And so as you can see with the fixed silicon doping density, as you increase the top in-gas barrier, you start filling up the electrons into the conduction band, as seen in the red. So motivated by this, we grew a sample where we had a 4 nanometer in-gas top barrier, and we introduced this 2 nanometer or 2 monolayer thick aluminum arsenide layer for the diffusion barrier. And we're able to, so we conducted low temperature magnetotransport on this sample at 1 Kelvin, and we saw that you can actually get an electron density of 1 times 10 to the 12 per centimeter squared. Electron mobilities that are exceeding 7,000, and you're starting to get these well-defined quantum Hall states, which signify that you just have a nice 2D channel for your electrons. So this, up until this point, we're able to say that we can grow good quality TUDEGs, relatively good quality TUDEGs, and we're able to grow aluminum layers on indium arsenide without this huge reaction. So what's next? So since the main motivation of these types of structures is that they will be better performing for microwave purposes, we wanted to test this by making coplanar waveguide resonators on these types of materials. So the first type of material that we tested was just sputtered niobium on silicon. And we know that these were supposed to give us pretty high internal quality factors. So as you can see, this is what we observed with quality factors above 1 million. And so this was a good check on whether our microwave setup was able to measure quality factors up to this amount. So that was a good check mark. The next was to fabricate resonators on our device, on our materials. So how we did this was we made resonators in this style, where we actually used the conducting region and the ground planes where this entire 3,5 bulk was included in the conducting region of the ground planes, and we etched down to the indium phosphide substrate. And then we did microwave transmission measurements. So doing it on this structure with the graded buffer layer, we expected this to be perform not that well due to the loss you get in the bulk because of defects in the graded buffer layer. And what we saw was that quality factors on this types of materials, you're only able to get quality factors up to a couple thousand. And so this definitely is not that good when you want to make qubit. You want to make qubit devices out of this material. The one thing is that when you're making a gate-mon device, you're actually not making it on the 3.5 itself, but you're making it on this. You're making it directly on the indium phosphide substrate. So as I was saying before, you have this extra etching step where you define your qubit island, and then you etch down to the indium phosphide substrate everywhere else. And then you have this recontacting step with the sputtered aluminum, where you go from the qubit island down to the indium phosphide substrate. So in order to give us a sort of upper bound for resonator quality factors on gate-mon devices, we measured resonators that were just sputtered aluminum on bare indium phosphide. And doing this in the red stars, you can see that we were able to get quality factors up to around 30 to 40,000. And this is consistent with resonators fabricated on indium phosphide. So that sort of gives us our upper bound for resonators on gate-mon qubit devices. And then finally, we were able to measure resonators on our new materials, the ones without the graded buffer layer. And doing them in this style, we're actually able to see resonator quality factors on the same order as those of just sputtered aluminum on bare indium phosphide. These are the blue dots. So we're pretty excited about this progress because, as I was saying, this sputtered aluminum on bare indium phosphide really only gives you an upper bound on how good your resonator quality factors can be on this old structure in gate-mon devices. Because of this extra etching and recontacting step, your resonator quality factors are only going to suffer and go down from there. So the fact that we can get quality factors on the same order as those which are more or less the upper bound for those on gate-mon devices, we're pretty excited about. So to conclude, we're able to identify aluminum arsenide as a diffusion barrier and grow epitaxial aluminum contacts on indium arsenide quantum wells. We're able to grow a strained 2D indium arsenide channel near the surface with electron mobilities exceeding 7,000. And we're able to show an enhancement in the microwave performance. And that's it. And I'd love to take some questions.
I have a
Yeah.
burning question.
Yes.
I'm a quantum noob, admittedly. So the others on this call may understand the implications of this better than me, but I'm curious, for the Army, what is the practical application of what you studied? How did they plan to use this?
So I think there are a number of good things that you can use this type of thing for. Once you have a fully fledged quantum computer, you can start doing things like logistics analysis, and there are a number of other things, drug discovery, materials discovery. The list is very extensive. We're not at that level yet, but I'm hoping that this type of material can sort of lay the groundwork for building high-performing quantum computers that can do these kind of things.
Thanks.
Hey, Billy, thanks very much. That was terrific. So your next steps, could you just put a little color around, what you're going to do next? Where you're going to take this terrific work?
Yeah, so the next steps are, so in the gate-mon qubit, you can't just have the resonator, you need a resonator coupled to a qubit, which is the Josephson junction. So the obvious next step is to show that we can get working Josephson junctions on this material. And then that you can couple the Josephson junction to a resonator and operate it as a qubit. Other next steps are to really characterize the types of losses in these materials. So as I said, one of them is that indium phosphide is known to be piezoelectric, but how piezoelectric is it and how will that limit gate-mon qubits on this type of substrate as opposed to something like silicon? And yeah, actually making the gate-mon qubits.
Cool. And is there a time frame for that? Not to hold you to it, but
Oh, no, it's okay. So we're currently working on fabricating code junctions. So that's hopefully as soon as possible, we can get some results on that.
cool.
The whole Gatemon qubit fabrication is definitely on a longer time scale than that, probably months to years. But yeah, hopefully before I graduate. And I
Great.
think, yeah, and the quantifying the types of losses in these materials is definitely another good next step for making resonators.
Great. Well, congratulations on this great work. Very cool. Thanks for sharing. I see you put a Gmail address. I put your school email address and your LinkedIn profile in the chat client. So if anybody wants to get a hold of Billy, information's in there. Please reach for him to learn more about this cool work. All right. So that was great. Let's move on. Our next researcher is Mitchell Yothers. Mitchell graduated from the University of Oklahoma in September of 2020 with his PhD in experimental condensed matter physics. Mitchell's been working on research in Dr. Lloyd Bum's group focused on high precision measurements of alkanethiol self-assembled monolayer structure with scanning tunneling microscopy. I hope I said that right, Mitchell. I hope I was close. Today he's going to be presenting, no, oh well. Today he's going to be presenting some of his research on post-processing correction of STM images of crystals. So Mitchell, over to you.
Thank you. Can everybody see my slides?
Yeah.
Okay. So yeah, thank you for the introduction. Today I'll be presenting my research on post-processing correction of STM images. I might go a little bit into the applications of the corrected STM images at the end. The more specifics of my research. But I'll start by showing how STMs acquire STM images with some background on how the tunneling feedback loop works, the STM controller, and the raster scan, and also some of the problems with STM image distortion. Then I'll go into how we do the post-processing image correction through a few steps. And then at the end, I'll show what you can do with corrected STM images to make great measurements. So starting with scanning tunneling microscope fundamentals, the way the scanning tunneling microscope works is you take an atomically sharp probe and you bring it very close to a flat conductive sample, and you put a bias voltage between the probe tip and the sample, and that causes a tunneling current proportional to the exponentially dependent on the distance between the tip and the sample. So if you get a little bit closer, you get a lot more current. We can use that in a feedback loop to determine to get a constant height of the probe above the surface. If the current's too low, that means the tip's too far away and we move it forward. That increases the current. If the current's too high, that means the tip's too close and we move it back. That decreases the current. And so if you do that and then move your probe along the surface, you'll get the probe tip constant distance away from your surface without touching it. You can image surface topography as long as you have homogeneous sample. And there's a image there in the bottom left that's an example STM image. It's colored black and white. White is high, black is low because it's a topographic image. It doesn't capture color information like a traditional microscope would. So it acquires the image in a raster scan because it's a scanning probe. It has to take the images one pixel at a time. So does that in a pretty straightforward method. It has to go over every pixel. So you start by taking the first one and you move in a straight line the whole way along the first row. Then you turn around and you come back along that row. So the first pass we call the trace and the second pass we call the retrace. We can compare those to confirm that our image quality is good. Once we've got the trace and retrace of the first line, then you move one pixel orthogonally to the next row and you repeat the process until you get the whole image required. We call the direction it originally starts scanning in, the fast scan direction, and the orthogonal direction, the slow scan direction, because for a 1000 by 1000 pixel image, it takes 1,000 times longer to move in the slow scan direction than the fast scan direction. There are some problems with this. We control the scanning probe microscope tip with piezoelectric actuators. The STM controller has a model for that that says when I apply a voltage, I get constant motion per volt applied. So this is the model it has. But in practice, the trace, due to piezoelectric actuator hysteresis on the trace, it does not follow this line. And on the retrace, it doesn't even follow the same line. It follows a completely different line. And so we need to take account of that for our distortion. So here's what it might do to an STM image. If you think of the left side as what the STM scan probe is doing, and as the right side is what you see on your computer screen. So the controller is scanning the tip at what it thinks is constant velocity, but it's actually not constant. And so that causes the one side to be stretched out and the other side to be squished. And exactly the opposite happens on the retrace. At the beginning, it's stretched out, and at the end, it's squished. And so you get images that are exaggerated here, but this is what might happen if you had hysteresis in your images. You can also have linear thermal drift. So I have a window that the STM scan controller is planning to trace, but if that window moves over the surface while I'm scanning it, then I get a distorted image. You can, if you know how it was moving, you can redraw it in you can draw here the window that it actually traced over. That's how we should be displaying this image, and not the blue square, and not in a square. We should be displaying it in this parallelogram, which we can get with the drift vector. So if you can do this, then you solve the problem. But you also have piezoelectric actuator creep, which looks just like drift, except with time-dependent drift velocity. So it starts moving really fast and then it's moving really slow. And so you get an extremely complicated shape. But if you break it down into parts, it's not too bad. I trust you that you'll understand by the end of this talk how we go through it. So all we got to do is show the image in this shape, and it's undistorted. So how do we do this image correction? We need to determine and apply the inverse transformation of the distortion. So we're going to measure the distortion at multiple points in the image to get the distortion trend with time, because we know the chronological order of the pixels. If we get distortion at a bunch of points in the image, we can plot them versus time and determine the time trend of the distortion. We know our nearest neighbor features in a lattice should lie on a circle. For our substrate, we are looking at graphite, so you got 6 carbon atoms and a close packed grid. So using some simple linear algebra, this is what the distorted, a single point in a distorted image would look like. It has some shear, it has some change in height, and it has some change in width. And using, if we could determine these parameters, we can transform back and forth between the distorted and undistorted images. So we get the computer to determine the feature locations for us. So that could be carbon atoms in a graphite lattice, or terminal groups of alkane thiols, or whatever features you're looking at in your scanning tunneling microscope image. We get a grayscale image like this, and using a cross correlation with a Gaussian, we can turn that into positively and negatively correlated areas, which we can use to fit to a shape model that simplifies the data quite a lot. And then index the features so we can look at statistics of individual features later. With those feature locations, we can determine how their positions are related to each other by example of finding nearest neighbors. So this is a radial distribution function of the feature distances from each other, and there's a big spike at exactly the nearest neighbor distance, so you can identify which features are nearest neighbors and fit a you can see before the distortion with the blue data, it's still works, but after the distortion correction, it gets much better. So once we have feature locations, so here's an example of how we would calculate the distortion. We wanted to calculate the distortion at this yellow point. So we get the nearest neighbor features in green. We find the best fit ellipse to them, which should be a circle in an undistorted image, but it's an ellipse because the image is distorted. We calculate the distortion that would cause a circle to become this ellipse, and we label the distortion at that point by that just that drift velocity vector. And we can plot that versus time and get a trend line for that, and there's the distortion that's affecting our image. This is scale correction versus fast scan time, which is a fit for hysteresis. So we used a fourth degree polynomial as a model for our hysteresis, which fit pretty well to the data. Then we also have fast scan drift velocity, which causes shear, and slow scan drift velocity, which causes stretch. And fit those to our data using some models for drift velocity and creep with a tiny little bit of acceleration, and that also fits excellently. So if we take these and apply these to our image, instead of a square image that's distorted, we get this output image that's much less distorted. And so here's a row of connected neighbors, which should obviously be a straight line in a lattice, and here's a straight line. You can see they don't overlap, but on the corrected image, the straight line and the connected neighbors do overlap. Just to wrap up, I'll show some applications of this. So here's a average unit cell image of an alkane self-assembled monolayer. It has a 4-molecule basis, so you can see 4 different colors of ellipses on this chart. Those are the 4 different molecule head groups you're seeing there. The way we got this extremely high resolution image is we have an image with tens of thousands of molecule terminal groups in it, and rather than showing them as 10,000 fuzzy images, you can reconstruct it instead into something like this, which is one extremely high resolution image, which is great for seeing the structure. On top of this, I have some ellipses drawn. Those are the deviations of the positions of the molecules from the lattice sites and the average unit cell. So you can look at this as a way to improve image resolution or a way to extract data from images. Both of them work great. I'd just like to acknowledge my advisor, Dr. Bum, and all the other members of the OU Physics and Tufts Chemistry group that helped me get some STM images on their cryogenic STM. And thank you for your time.
Thank you, Mitchell. That was great. Are there any questions? We'll open it up. Unmute or type them into the chat. Questions for Mitchell? Let us know. Also, Mitchell, I put a link in the chat to your university website that has a couple of publications that are available, right? So if people want to follow up and learn more about the work that Mitchell's doing, check out the links in the chat. Okay.
Yeah, I'll ask a similar question that I asked for Billy as well. How do you hope to see your research applied in the real world?
I think the scanning tunneling microscope is an amazing instrument that can really make some great measurements. But right now, it is not being used in industry applications. And I think part of that is due to the fact that it can be, because of the distortions, it's hard to make good measurements. And so I would hope that being able to make good measurements with the STM would make it useful to people trying to do things, make small things in industry. an extremely exciting upcoming field is nanofabrication, where you make things out of atoms instead of tearing things down to make something, you build it up. And good measurement tools are necessary to start doing something like that.
Great. Well, thank you. Again, I put your email address and your LinkedIn profile in the chat. So if people want to follow up with you and continue the conversation, they can certainly do that. So thank you, Mitchell. Moving along, our next researcher is Dengyu Yang. Dengyu is a graduate student researcher at the University of Pittsburgh in the Department of Physics and Astronomy and the Pittsburgh Quantum Institute. She received a bachelor's degree from Beijing Institute of Technology in 2016. Then she's pursuing her PhD in experimental condensed matter physics in Dr. Jeremy Levy's research group at UPIT until now. Her research interests center around the emerging field of oxide nanoelectronics, experimental realizations for quantum computation, quantum transport, and dynamical phenomena in oxide materials and films. So Dengyu, over to you.
Okay, thank you, Chris, and thanks for having me. I'm Dengyu from Dr. Jeremy Levy's research group in UPIT, and first of all, I would like to thank our funding resources and our collaborators from Wisconsin, Chanbang Young and Dr. Ben Hunt from CMU, who provide our LLSU samples and the graphene exfoliated samples. So thanks. My topic today is on our efforts on the nanoscale control of the metal insulator transition using ultra-low voltage electron beam lithography at lanthanum illuminate strontium technique. Quantum science is a big topic for modern physics, and for many years we're facing the grand challenges and open questions to the quantum engineering and science, and questions like how can we do quantum computation, and there are methods as superconducting qubits, and how can we achieve quantum simulation, and we have ion traps, ultra-cold atoms, and many other methods, and others like quantum sensing and quantum metrology. And for us, we believe that the controlling quantum matter lies at the center of all these grand challenges. And the quantum matter here I'm referring to is the lanthanum illuminate strontium titanate heterostructure, which has rich phenomena that have been discovered. When the LEO growing on SCO substrate, there will be a high mobility 2D electron gas formed at the interface, and it has the metal insulator transition, superconductivity, magnetism, and tunable spin orbit coupling. All these properties makes this system a great platform for quantum electronics. And with the metal insulator transition, our group has developed a technique called the conductive AFM lithography at the LEO-STO interface, which can be used to pattern nanostructures such as nanowires and tunneling barriers at the interface. To do that, we start from the 3-unit cell LEO on STO substrate, which is insulating but highly tunable, and the titanium and gold are here acting as the interface contact. When we apply a positive voltage to the AFM tip and drag it along the top surface, it will leave a path of protons. These paths of protons will act like a local top gate, tuning the interface below the path through metal insulator transition. This writing process has a very high resolution. The width of the wire can be as small as 2 nanometers, and it's also reversible, which means we can simply erase it by applying a negative voltage to the tip and drag it and erase the device. So with these technique, we have created many different devices at the LEO-STO interface and exploring the properties of the LEO-STO interface. And things like we can do single electron transistor at the interface, and we observe the electron pairing without superconductivity. We can combine these with the graphene and to do graphene complex oxide heterostructures, and we also observe the tunable electron-electron interactions. We have electron waveguide with ballistic nanowires, and we observed the 1D nature of superconductivity, and most recently, we observed the Pascal conductance sequence, and all of these are really good results from our group. But as we're taking advantages of the conductive FM lithography, we're also facing the limitations it has. So I summarized these into the writing efficiency issues. So for the conductive FM lithography, the writing speed is in the range of 10 nanometer per second to 1 micrometer per second. And at the same time, the device itself is decaying naturally in the air on the timescale of hours. So these two conditions restrain the complexity of the device we could make. At the same time, the writing scale is like literally limited by the AFM scanning size, which is 90 by 90 micrometers is the largest one we have. So these conditions makes the conductive AFM sufficient for us to explore such as one-dimensional devices, but not when we want to like expand to two-dimensional. It's not that enough for us. So to overcome these kind of limitations, I would like to introduce the ultra-low voltage electron beam lithography here, which also can be used to pattern connecting nanostructures at the interface. But at the same time, it introduced the speed boost and size explosion of the writing process. The writing speed can be up to 10 millimeter per second, which is 10,000 times the writing speed of the conductive FM lithography. And the size can be as large as a wafer. And here we use the ultra low acceleration voltage, which is at around 100 volts range to avoid the damage to the oxide structures. And during the exposure, it's in a vacuum condition. So that makes the device preserve itself in the vacuum for like longer lifetime. And more interestingly, we found we can combine this method using right through a thin layer on top of LUSTO, such as we have a graphene or boron nitride graphene stacks on top of LUSTO. We are still able to write through it and creating connecting structures at the LUSTO interface. And we published our preliminary data on APL, and it's selected as the cover and featured article on that issue. So please take a look if you're interested. So this is to show the writability of this method. To do that, we have electrodes at the interface, and we expose a nanowire connecting these two electrodes using the ULV EBL. And with this writing process, we can observe a conductance jump from the writing. This monitoring is the in situ monitoring. We add the electrical feed through to the SEM so that it allows us the in situ electrical measurement during the exposure. And this writing process is also reversible. So when I transferred it into an AFM and apply a negative voltage to the AFM tip and erase it, this device can be erased totally. And it's naturally to ask what's the resolution of this writing process once we have a way to write the devices. So to explore that, I have a bunch of nanowires which separated by 5 micrometers, which are the distance are large enough to suppress the crosstalk between nanowires. And I have a gap in the middle of the nanowire, and I'm varying the gap size. As the gap is getting smaller and smaller, at some point, the gap will be like covered by the resolution. And we found the resolution of the writing is at around a sub-10 nanometer scale, which is comparable with the conductive FM lithography. And also we did some transport measurements to the device we created, and we observed the superconducting behavior below 200 millikelvin, which is consistent with other LUSTO reports. And this is, as I mentioned, we have graphene on top of LUSTO. Here it shows we transferred the CVD graphene onto the LUSTO using wet transfer. And this is the AFM of over the graphene, and we can still see the terraces of the STO to show the graphene quality. And by applying these, exposing this nanowire, we can see a clear conductance jump from this writing process, which shows we can create nanostructures at the LUSTO interface underneath the graphene. And more recently, with the help from Ben Hunt from CMU, we have exfoliated graphene and boron nitride stack which will provide better graphene qualities. And we transferred it onto the LOSTO structure, and also we're exposing these nanowires, and we can observe a conductance from this writing process. And this is an optical image from a typical sample we have. So with all these results, we also purchased our own EBL system. So this is a Zeiss Gemini 450 SEM, and it will give us better low voltage performance and will fit our use, fit our requirements better. And we add the electrical feed-through to it with dual 28-pin socket and the electrical measurement to it. So we're really looking forward to more new results from our new system, and we already established it. And in summary, I showed that the ULV EBL can use to create LOSTO nanostructures, and it shows the superconducting behavior. And we can even write through a thin layer on top, the boron nitride graphene and the graphene, and we have the new instrument. We're really looking forward to combine these methods with other multi-layer van der Waals materials, and such as we can do dynamic gating the graphene using the LOSTO nanostructures underneath the graphene, these kind of interesting experiments later on. And that's all. Thank you.
Well, thank you. Dengyu. That was fascinating, amazing work that you're doing.
Thank you.
Thank you for sharing. Any questions, put them in the chat or unmute your mic and post questions.
I had a question.
Yeah.
How thick was the LAO?
3 units cell. So
3
around
units cell.
1.2 nanometers.
And it's like commercial STO substrates with LAO grown on top?
Yes, exactly. We do a termination on the STO to make it TIO to terminate it, to make sure the quality of the 2D electron gas. But it's a commercial STO substrate, and it's the PLD grown LAO on top.
Okay. How does the TiO3 termination work?
You mean how do we create the TIO to terminate?
Yeah, how is it done?
I think it's using the HF, and I'm not exactly sure because it's done by Changbaum's group from Wisconsin.
Okay, cool.
Thank you.
So, Dengyu, maybe you can connect Billy with the group in Wisconsin,
Sure.
right, to get that answer. That'd be great.
Yes.
And any other questions for Dengyu? No. And again, I put Dengyu's email and LinkedIn profile in the chat, so please feel free to reach out to her and follow up with any questions you might have. All right, great, thank you. So moving to our final researcher of the day, Patrick Kelley. Patrick is a PhD candidate in the physics department at Indiana University, Purdue University, Indianapolis. He's working under Professor Ricardo Deca. Patrick is working in precision measurement in the search for new forces. Specifically, he's trying to probe for gravitational deviation from Newtonian gravity at really small distances that may begin to explain why gravity, out of the 4 fundamental forces, fails to fit into the standard model that already successfully incorporates the other 3 fundamental forces, i.e. electromagnetism, weak and strong interaction. So Patrick, thank you for joining us. Over to you.
All right, just trying to
There
get
you
the
are.
share screen to work.
No worries.
Let's see. Laser pointer.
I find sometimes the problem is having too much stuff open on your computer. There you go.
There you go. Which one are you guys seeing the presentation?
Yeah.
Yes.
Okay. So I'm Patrick Kelley. Thank you for the introduction. So I'm working on trying to cool a quantum dot for the purpose of weak force sensing. There you go. So what is the force that we're trying to sense? It's gravity. And you might have heard of all of these strange things like dark matter and dark energy and all of these things. And so it kind of hints that there's something outside of just our normal Newtonian gravity, which has worked very well for most of our ranges. Of course, once we go big enough, that's where general relativity kicks in. But then the question is what happens when you get really small distances? So you start, zooming in. And we're going to just pull up something from the particle physics textbook, and we're going to add a Yukawa-like model here, where the alpha denotes the strength of this interaction, and the lambda here denotes the characteristic length at which it starts kicking in. And the challenge here is that gravity is very, very, very weak compared to other fundamental forces, such as what we always interact with is electromagnetics. So the question then comes is, how do we measure it? And really fundamentally, we have to decouple our mass from our environment. That's the biggest thing we have to do. And how we're proposing to do this is using optical tweezers. So we're going to levitate this in a beam of light. And this comes from the works of Arthur Ashkin, who got the prize in Nobel Prize in Physics in 2018 for that work. So a quick rundown of Gaussian beams. So this optical trap, the core takeaway of all of this fancy math is that at the maximum intensity at this focal point here, the harmonic trap, this beam of light starts acting like a simple harmonic trap, like with a spring constant. And the spring constant is dictated essentially by the power of the laser, as well as the numerical aperture of the lens and the wave length of light. So what are the fundamental limits of this thing? So I'm on resonance, so at the peak of our spectral amplitudes, what we're looking at is the contributions that would contribute to this spectral profile. And we have imprecision, recoil, and thermodynamics. So I'll cover imprecision and the recoil in a later slide. But the leading term, the largest contribution, would probably stem from this thermal part here. So this would be basically our upper limiting contribution. And so this is going to dominate our spectral signature here. And if we're looking at that, what is the minimum force that we can detect given this thermal spectral distribution? It's going to be dictated by the center of mass temperature, meaning the way it oscillates around. This is distinctively different from the internal temperature, which is basically if it's becoming really hot, like red hot. So this is the motional temperature of it. And so to get a weaker force, to be able to measure definitively a very small force, you have to lower your center of mass temperature. So that leads us to really, that's the holy grail of this whole thing, is to get the maximum enhanced sensitivity. And mind you, this was in a harmonic trap. So it's approximately a harmonic trap. And if you get cold enough, so you get to your limiting factor, you're going to start approaching a quantum mechanical system. So it's a quantum harmonic trap. And so if you start approaching the discrete energy levels of your harmonic trap, what is the effective temperature that we have to get to in such a way that we would be able to start seeing this? And putting in some reasonable parameters of 100 milliwatts, our mass system that we're going to be playing around with a quantum dot, and a very high numerical aperture lens, we're getting something in the microkelvin regime. So we have to cool this particle down to microkelvins. So why particularly a quantum dot? And the interesting thing that my previous colleague of mine here at IUPUI did research on was that the power of a quantum dot, you have a cooling term that you can put to it. So the quantum dot, if you shine a certain light on it, will actually cool the internal temperature, meaning that you can increase the power of the laser that is trapping the particle. And that also has to do with the polarizability of the particle, where here's our quantum dot versus in most literature, you have a silicon dioxide or silica bead. For us, we're going to be playing with a cadmium sulfide, cadmium selenide quantum dot, which is going to be of the order of 5 nanometers. And the real interesting part is this imaginary part of it, which that is what contributes to how much power of the laser that the particle is going to absorb and heat up. So depending on our imaginary part of our polarizability, which depends on our dielectric, that will play a role in how much power we can put into our laser, and of course also have a cooling term as well. So we can put more power, which means a stiffer spring constant, which means a lower temperature. So I pulled up some data on optical properties of the cadmium selenide, cadmium sulfide, and cadmium selenide here. And with the wavelength of light that we're going to be using, there's missing data. We don't know exactly the imaginary part of the dielectric, which plays a role on our polarizability, that we're going to have. It's all that we can tell is it's very low, which is a good thing because we don't want any of the light really to be absorbed by the particle. We want it to not absorb anything or heat up or change its internal temperature. So this is an experiment that we have to do to determine what this polarizability, what this dielectric constant is. So to get an educated guess at what that is, what I did is I looked at the thermal steady state of the nanoparticle, where I equate all of the powers that would play a role in the internal temperature, namely the power that the laser would be absorbing, which depends on the imaginary part of the dielectric, the black body absorption, black body emission, the power that is dissipated by the gas. Because of gas collision, it will take away some of the thermal energy, the internal energy of the particle, and also of our cooling. Which I mentioned was done by a colleague of mine named Bunchuan Hua, and he found this cooling power. And so making an educated guess at, having a very low imaginary part of the dielectric, which plays a role in the polarizability, we're speculating that we can reach a maximum power, maybe of something of 100 milliwatts to maybe even something over a watt. So the cooling techniques that we're going to be using is an active one, which is a parametric feedback cooling. And the simple idea is basically a swing, and at the peak, you push it so that you're slowing this swing down. And it works perfectly if you can be able to, precisely know where exactly it is at any time. So the detection efficiency is essentially 1. So that's like a classical system, like you know exactly where that swing set is. And that P max is the modulation of our power that we're going to shift, such that we can cool it such that when it's at the lowest, we'll increase the power to the maximum spring stiffness of our trap. And once it reaches the maximum position, we decrease it so that it swings back at a lower force. But since our detection efficiency is not perfect, we're not in a perfect world, we basically reach a point where we do wrong pushes at the wrong time or wrong tugs at the wrong time. So essentially with active cooling, with parametric feedback cooling, we will reach a baseline temperature, and it's not going to be at the microkelvin range. So what we're going to do is we're going to switch, after using this and getting down to our baseline temperature, we're going to switch over to a cavity cooling. And a cavity cooling is unique in that the polarizable particle actually changes the electric field inside the cavity, and it just does so automatically. So as you can see by this illustration, it's modulating this the standing wave in the cavity in such a way that it's cooling the particle through its interaction with its polarizability. And just a quick note on the detection efficiency that I mentioned before, it's basically the dipole radiation that we're collecting. It's the ratio of dipole dipole radiation that we're collecting over the overall dipole radiation. And that's given really by our numerical aperture of our detecting lens. So one last thing that we can look at in our limiting term for our minimum force that we can detect is the cooling rate. And so there is a playoff between the imprecision and the recoil. The imprecision is the imprecision in our detection. So, you know, given Heisenberg's uncertainty principle and our overall detection efficiency, we can't see it perfectly. There is a little bit of noise because of that. And on top of that, there's recoil, which is because of the photons are imparting momentum on our nanoparticle. It actually, you know, it pushes it a little bit here and there. So the best cooling is where this is equal to each other, so that the imprecision is actually inverse to the recoil. And essentially what we're looking for is this intersection between the recoil here, which increases with more power you put into it, right? The more momentum it's imparted on our particle, and the imprecision, the more light you put into it, the better you can see it, right? So there's a trade-off between the two, and the best point is the intersection of the two. So that is the optimal cooling rate that we're going to try to reach. And so our basic experimental design is essentially we'll be bringing our nanoparticle close to a massive source, which is going to be one of the reflecting surfaces of the cavity. We'll be trapping it at one of the minimas of the standing waves inside the cavity. And we're going to be using a detecting lens here to track the position of it using a homodyne technique, a homodyne method. And given some of these, you know, reasonable parameters, we're estimating that we're going to get a minimum force of 10 to the minus 27 newtons. I forgot to put newtons here. And what I want to do is equate this to the UCO-alike potential that we have beforehand, where what this is going to be dictated by is our alpha, the strength, and the characteristic length. So how close do we have to bring it before this term starts kicking in? And we can observe some deviation from Newtonian gravity. And this is the last slide, which tells you this is what the alpha, the strength, versus the characteristic length that we can see improvement on from previous experiments. So this is all of the previous experiments that have excluded any deviation. They've never seen any deviation from Newtonian gravity in this parameter space. And so what hopefully our experiment will do is expand this map to exclude a lot more of the space. And these are all, you know, the possible physics that is trying to describe any of these deviations that are hinted at that they should exist, right? That that's the interplay between quantum mechanics and gravity. And that's basically concludes my presentation. I also want to give an acknowledgement to my advisor, Ricardo Deca, here at IUPUI. And I'm free to take any questions now.
So Patrick, thanks very much. That was terrific. There is a question from Charles in the chat. I can read it to you. It says, quantum sensing is a great area of research. What practical aspect are you, looks like, using to achieve with your gravitometer? Are you targeting the elusive axion particle from black holes?
That could be something, but that would depend on an axion that we would be able to measure. So unless it's a uniform field that we just penetrates our space, it's not really like like all of the axion particle physics, like xenon detection and all of these things, where it bumps into it and creates some kind of interaction. So with axion particles, probably not. What we're doing is more of just seeing if there's any deviation from gravity. And the other thing that we could be doing with this is, because we're bringing a semi-classical particle down into a quantum description, you can also use that to probe quantum mechanics for a massive object. So it's always been, atom scales. Atoms basically become a wave-like property. It starts becoming a wave function. And it's not classically described. I mean, quantum mechanics is purely quantum mechanics in that sense. So with this, you have a classical particle but in a quantum world. And so we can start mapping out, what happens with the, classical system in a quantum description. So we can kind of see all of like a Schrodinger cat and all of these other dynamics that could happen at that scale.
Great. Well, Patrick, thanks very much. I want to say thank you to all of our researchers, to Billy, to Mitchell, to Dengyu, and to you, Patrick. I want to mention that today's session has been recorded. We're going to share the URL with all of you as soon as it's available. Our next poster session is June 22nd. I'm going to post a URL in the chat for the calendar, and maybe you can join us at our next session as well. We'd be delighted to have you participate. Celia, turn it over to you just for a final comment.
Thank you, Chris, and thanks to our speakers today. I'm a reformed material scientist myself, so I really enjoyed hearing about all the work that's going on, and look forward to seeing you all move forward in your careers. I know we're at the end of the hour and we'll wrap it up here and adjourn formally. I'm happy to leave stop recording and leave things open if you want to stay on a little longer and have an informal visit like we would if we were at a normal meeting. So I want to thank you again and encourage all of the folks who are here from our industry members to come back for these events where we share with you some of the great talent that's coming out of the QED-C universities, and look forward to having more of these events in the future. So thank you, everybody. And with that, I will end the meeting and we'll go into the informal part if anybody wants to stay. Thank you very much.